Hello my dear students, today we are going to learn about the diagonal relationship and anomalous behavior of first member of each group. The first members of each group shows anomalous behavior. It is due to low atomic and ionic size, greater charge density, that is charge by volume of the atom, greater polarization and absence of d orbital. Greater polarization make the first element more covalent and differentiate them from the rest which are ionic. The similarity in size and charge density makes them resemble the element diagonally placed in the next group. This is called diagonal relationship. That is, some elements of certain groups of second period resemble much in properties with the elements of third period of next group. That is, elements of second and third period are diagonally related in properties. This phenomenon is known as diagonal relationship. Lithium and magnesium show diagonal relationship. Beryllium and aluminium show diagonal relationship. Boron and silicon show diagonal relationship. Then what are the reasons for the anomalous behavior of lithium? It is extremely small, greater polarizing power of ion, least electropositive character among alkali metals, and non-availability of d orbitals in lithium. Then the anomalous behavior of lithium and its diagonal relationship with magnesium. Here, the melting and boiling point of lithium are comparatively high. Lithium is much harder than the other alkali metals. Magnesium is also a hard metal. Lithium hydroxide, like magnesium hydroxide, is weak base. Hydroxides of other alkali metals are strong bases. Lithium reacts with oxygen least readily to form normal oxide, whereas other alkali metals form peroxide and superoxide. Due to their appreciable covalent nature, the halides and alkyls of lithium and magnesium are soluble in organic solvents. Unlike elements of group 1, but like magnesium, lithium forms nitrate with nitrogen. Lithium chloride is deliquescent and crystallizes as a hydrate, lithium chloride monohydrate. Other alkali metals do not form hydrate, but magnesium also forms hydrate, magnesium chloride octahydrate. The carbonates, hydroxides and nitrates of lithium as well as magnesium decompose on heating and give corresponding oxides. The corresponding salts of other alkali metals are stable towards heat. Lithium nitrate on heating decomposes to give lithium oxide, whereas other alkali metals nitrate decomposes to give corresponding nitrite. Unlike other alkali metals, lithium reacts directly with carbon and to form an ionic carbide. Magnesium also forms a similar carbide. Lithium carbonate, lithium hydroxide, lithium fluoride and lithium phosphate are the only alkali metal salts which are insoluble in water. The corresponding magnesium compounds are also insoluble in water. Hydrogen carbonates of both lithium and magnesium cannot be isolated in solid state. Hydrogen carbonates of other alkali metals can be isolated in solid state. In this way, lithium shows diagonal relationship with magnesium. This arises mainly because of their similar atomic and ionic size. The next topic is the anomalous behavior of beryllium. It is due to the small size and high polarizing power of beryllium, relatively high electronegativity and ionization energy as compared to other members of alkaline earth metals, and the absence of vacant d orbitals in its valence shell. The anomalous behavior of beryllium includes: beryllium is much harder and denser than all the alkaline earth metals. It has higher melting and boiling points compared to other elements in group 2. The oxides of beryllium are amphoteric, whereas other oxides of alkaline earth metals are strong bases. Beryllium do not impart color during flame test. Beryllium carbide reacts with water to give methane, whereas carbides of other alkaline earth metals gives acetylene gas. Beryllium forms covalent compounds, whereas other members form ionic compounds. Beryllium reacts with water very slowly, while magnesium reacts with boiling water, and others decompose water at ordinary temperature and liberating hydrogen. Beryllium does not exhibit coordination number more than 4 as it has 4 orbitals in the valence shell. The other members of this group has coordination number 6. Beryllium forms covalent compounds. Beryllium oxide does not react with water, but other group metal oxides react with water and to form sparingly soluble hydroxide. The next topic is the diagonal relationship between beryllium and aluminium. Unlike group 2 elements, but like aluminium, beryllium forms covalent compounds. The hydroxides of beryllium and aluminium are amphoteric in nature, whereas those of other elements of group 2 are basic in nature. The oxides of both aluminium and beryllium are high melting insoluble solids and show amphoteric character. Beryllium chloride and aluminium chloride have bridged chloride polymeric structure. Both are Lewis acids and used as Friedel-Crafts catalyst. The salts of beryllium as well as aluminium are extensively hydrolyzed. Carbides of both the metal reacts with water and liberating methane gas. The oxides and hydroxides of both beryllium and aluminium are amphoteric and dissolves in sodium hydroxide as well as in hydrochloric acid. Like aluminium, beryllium is not readily attacked by acids because of the presence of an oxide film. Beryllium and aluminium forms a nitride with nitrogen. These nitrates react with water and to yield ammonia. The next topic is the anomalous properties of boron. Boron is the first member of group 13, which shows anomalous behavior due to its extremely low atomic size, high nuclear charge to size ratio, high electronegativity, and non-availability of d orbitals in the valence shell. Anomalous behavior of boron includes: boron is a typical non-metal, whereas other members are metals. Boron is a bad conductor of electricity, whereas other metals are good conductors. Boron shows allotropy and exists in two forms, crystalline and amorphous. Aluminium is a soft metal and does not exist in different forms. Like other non-metals, the melting and boiling point of boron are much higher than those of other elements of group 13. Boron forms only covalent compounds, whereas aluminium and other elements of group 13 form even some ionic compounds. The hydroxides and oxides of boron are acidic in nature, whereas those of others are amphoteric and basic. The trihalides of boron exist as monomers, but aluminium halides exist as dimers. The hydrates of boron, that is boranes, are quite stable, while those of aluminium are unstable. Dilute acids have no action on boron, others liberate hydrogen from them. Borates are more stable than aluminate. Boron exhibit maximum covalency of 4, while others exhibit maximum covalency of 6. Boron does not decompose steam, while others decompose. Boron combines with metals and to give borates. Other members form simply alloys. Concentrated nitric acid oxidizes boron to boric acid, but no such action is noticed in other group members. The next topic is the diagonal relationship between boron and silicon. Boron exhibits resemblance with its diagonal element silicon of group 14. Both boron and silicon are nonmetals. Both are semiconductors. Both boron and silicon form covalent hydrates, that is, boranes and silanes respectively. Both form covalent and volatile halides which fume in moist air due to release of hydrogen chloride gas. Both form solid oxides which get dissolved in alkalis, forming borates and silicates respectively. Boron and silicon shows allotropy and exist in two forms, crystalline and amorphous. Both boron and silicon are not attacked by water or non-oxidizing acids. Both boron and silicon can be prepared by reducing their oxides with magnesium. Both boron and silicon reacts with oxygen at high temperature. Both oxides have high melting points and are acidic in nature. Both boron and silicon combines with sulfur at elevated temperature and to form their sulfates. The chlorides of both the boron and silicon get hydrolyzed by water and to give boric acid and silicic acid. The fluorides of both the boron and silicon get hydrolyzed by water Boron trifluoride yield orthoboric acid and fluoroboric acid, while silicon tetrafluoride yields orthosilicic acid and fluorosilicic acid. Today we have discussed about the anomalous behavior of lithium, beryllium, boron, and its diagonal relationship with magnesium, aluminium and silicon. In the next part, we will discuss about the general characteristics of group 15 elements. Thank you.